Hello. Good afternoon to all of you. Am I audible? Hello. Am I audible to you?
Yes, sir.
Okay, thank you. So today we would be a little bit take some topic of the theory as well. Means two technique we will be learn, and then after we would be see the practical of QPSK. So and tomorrow we would be learn the last topic of the unit number 5. So how many students are joined? So first of all, we have to be start with the topic of MRE, PSK that we have also started in the last lecture. Some points we have seen already, but I am going to repeat today here. So we have learned the BPSK technique where we have used the binary symbols, and that is 1-bit symbols are actually 0 or 1. But when in some applications we have to be required to combine these bits to make a symbol that consists of multiple bits. So similarly, that technique is called as the MRE signaling techniques that we have already learned in the unit number 4. So here, if you have to talk about the MRE PSK, in BPSK generally we transmit each bit individually, depending upon whether the BT or digital signal is or polar energizer signal is logic 0 or logic 1. We transmit one or another of the sinusoid for bit time TB. The sinusoids differing in phase by the amount of 2 pi upon 2, that is equal to 180 degree with each other. And when we have to be proceed and move to the QPSK technique, where we have lumped the two bits together, depending upon which of these four 2-bit words would be developed. So when we combine the two bits, there is a 4 possibility of these 2 bits has been developed. And when we transmit these 2-bit words, one or another of the 4 sinusoids of duration what? 2 TB. So here the duration of transmission would be increased, and also the sinusoids differing in phase by the amount of 2 pi upon 2 raised to the power 2, means 2 pi upon 4, that is 90 degree. So here phase shift would be between the two symbols is decreased, that is 90 degree only. As well as the bandwidth is also decreased. So in the similar fashion, in QPSK we have combined only 2 bits. If we have to be combined n number of bits, so that there is a n bit symbol would be generated, and this n bit symbols extended over the n TB time period, and there are possibility of the 2 raised to power n in possible symbols. Okay, so now let us represent the symbols by the sinusoid of duration n TB, that is equivalent to the symbol period, that is TS. TS is here and TB, which differ from one another by the amount of phase, that is 2 pi upon m. M is what? 2 raised to the power n. So here total phase between the phase shift between the two symbols are there, 2 pi upon 2 raised to the power n. Thus, in MRE PSK, the waveforms used to identify the symbols are can be represented mathematically by the equation ST is equal to square root of 2 PS cos 2 pi f naught t plus phi m. So what is the phi m is here? M is here. And this could be a natural number, that is 0 to m minus 1. Okay. So there is a phase shift of phi m is here. So what is the phi m actually? It is 2m plus 1 pi upon capital M. So the symbol phase angle is given by the equation phi m is equal to 2m plus 1 pi upon capital M. So m is here 0 to m minus 1. And this m is what? 2 raised to power n. On the right side also the signal space diagram is also shown of this MRE PSK. We will come to later on. So the orthonormal waveforms here, that is the carrier signals actually. Phi 1t and phi 2t. Phi 1t is a cos wave, that is given the equation number 3, and phi 2t is a sine wave, that is square root of 2 upon ts sine 2 pi f naught t. If you have to be see this representation of the this orthonormal carrier signals on this signal space diagram, so you would be found that in the MRE PSK there is a possibility of the m number of symbols, that is 2 raised to the power n number of symbols are there, that could be represented with the help of this circle, and this all symbols that is start from the V0 to Vm minus 1, that would be located on the circumference of this particular circle, means it is equidistant from the origin, and the distance between or phase angle between these two consecutive symbols are 2 pi upon m. If it is m is 8, means 8 PSK, so it is 2 pi upon 8. If it is 16, 2 pi upon 16, like this. If it is QPSK, 2 pi upon 4, that is pi by 2. So depending upon the value of m, okay, so it would be phase angle would be varied. As the number of bits would be increases, the phase angle is decreases, and the distance between the two signal points would be decreased. So it would be start from the this part of pi m, 2 pi m, like this 3 pi m up to the in this way. So here in the x-axis I have shown the cos wave of carrier function u1t or phi 1t you can say, and then in the negative y-axis you have to see the phi 2t. Okay. Now in this way we have to be see, and if we have to see the distance of this signal points from the origin or reference point is, that is nothing but square root of es or square root of psts, that is our general, we have seen the distance in the case of signal space representation. Now we have to be find out the Euclidean distance and as well as the bandwidth of this signal. So we have to be derive the distance of h dot from origin, that is you can say es square root of es, that is square root of ps ts, that is in terms of power form. So from the equation 1 we have st is square root of 2 ps cos 2 pi f naught t plus phi m. So we know that this is the formula of cos a plus b, that is cos a into cos b minus sin a into sin b. So using same formula we have to be elaborate this equation st square root of 2 ps cos phi m into cos 2 pi f naught t minus square root of 2 ps sin phi m into sin 2 pi f naught t. This is equation number 6. Now we have to be defining even and odd bits p and p naught. So p is what? Square root of 2 ps cos phi m, and p not any odd function is square root of 2 ps sine pi m. Now substitute this p and p naught on the equation number 6. So you would be got, noted down these equations. So when you have to be substituted these two values on the equation number 6, st would be become p cos 2 pi f naught t minus p naught sine 2 pi f naught t. That is equation number 7. If you have to be see, both p and p naught can change after every symbol period, that is ts is equal to ntb, and it could be assume any of the m possible values. So this is the description of the signal space diagram of the MRE PSK. Now on the basis of that, we can also find out the bandwidth of MRE PSK. If you have to be see, the bandwidth is what? It is 1 upon FB, TB, actually 1 upon TB, 1 upon NTB actually. So you can also write it as in terms of symbol period and bit period as well. B is equal to 2 upon TS, that is 2 upon TS is what? NTB in terms of bit period. That is, you can say bandwidth is nothing but 2 times of symbol frequency Fs, or 2 times of bit frequency upon capital N. This is also very important relationship. So what this equation number 8 says that, the equation number 8 says that as the number of bits would be increases in the MRE PSK, means the value of n would be increases, the bandwidth would be decreases. Okay, so for the case of BPSK, you can define it is bandwidth n is equal to 1, it is 2 of FB. QPSK, n is equal to 2, so you can say FB, like that. You can, bandwidth will be further could be decreased if you have to be increase the number of n, or number of bits actually per symbol. Number of bits would be increases, your bandwidth would be more smaller and smaller. That is our objective, to decrease the bandwidth and power requirement for any modulation technique. Now if you have to be further, we have find out the bandwidth. Now we have to find out the Euclidean distance from this diagram that you have taken, signal space diagram of the MRE PSK. So if you have to be refer this diagram, the Euclidean distance could be came as, you have to once again refer this diagram, then the picture would be more clear. So what is the Euclidean distance in this particular signal space diagram? If you have to be see, this is nothing but the distance between the two signal points. That means this is, so here radius is same, means root under ES, root under ES is there. So this is nothing but a sector. You have to remember the formula of sector. There's a angle you can consider and draw right angle triangle here, and in this way you can find out this from the formula of sector. So it would become as, I'm not going to detail mathematics, this is not our concern. So that distance would become as mathematically d is equal to square root of 4 ES sine square pi upon capital N, means 2 into square root of ES sine pi upon M. Or in terms of, if you have to write it in terms of N, so it would be 4 N EB, because symbol energy could be converted into the bit energy. So it would be ES is nothing N times of EB sine square pi square to raised to power N. Okay. So this is also very important formula, equation number 9, where you can see the symbol energy is ES. It could be written in terms of bit energy, that is EB. So it is PS, TS means TS is NTB, it is PSTS. So it would become as NEB. This is also very important relationship between the symbol energy and the bit energy. So EB is what? It is the energy associated with the one bit. Okay. After this analysis of signal space diagram as well as the bandwidth of the memory PSK, now we have to see the structure of transmitter and receiver of the memory PSK. Means generation and detection of memory PSK. So first of all, we have to see memory PSK transmitter. You can see it is a very simple block diagram I have shown. Actually, it is very much complex, but for the simplicity, I have only used the blocks, not the detailed components of the circuitry. So you can see the bit pattern. Please all of you note it down. And this diagram is taken from the top selling book. You can also refer that book for this all unit number 5 for generation detection of all kinds of the modulation techniques. So here the bit is what? Bit is bit stream. It is applied to a serial to parallel converter, and this converter has the facility for sorting the n bits of a symbol, n bits information of a symbol. We know that we are learning about the memory PSK, where we are combining the n number of bits to make a symbol. The first symbol, there is a n number of bits. So this serial to parallel converter having the facility for sorting the n bit symbol, and these n bits have been presented serially to this system, and that is you can say in the time sequence one after another. So these n bits having been assembled and then presented at once on the n output lines of the converter, that is presented here parallelly. You can see this serial input of n bit would be presented to the digital to analog converter parallelly by each separate n number of lines, 0 to n minus 1. Sure. And this converter output remains unchanged for the duration of n TB. That is a symbol duration, TS. And up to this n TB time duration, it would be remains unchanged, this information, because during this duration it would be converter would be assembling a new group of n bits information. So once the n TB time would be elapsed, this information would be moved forward, and the next n bit information would be ready for the conversion. Now this parallel data, or you can say the serial to parallel converter output symbol would be given to the digital to analog converter, where the digital to analog converter generates an output which is assumed to be one of the 2 raised to power n or m possible symbols applied to the inputs. So this VSM is nothing but it is one of the m number of symbols. So digital to analog output is a voltage signal, that is VSM is mentioned here, which depends upon the value of symbols. VM is equal to, where VM is VM, that is m is here equal to 0, 1, 2 up to m minus 1. So it could be any of the voltage signal for any of one of the symbols of the out of m symbols. Okay. So finally, this symbol has been fed to the applied to a control input, that is a sinusoidal signal source phase controlled in block is there. So it would be applied as a control input to a special type of the constant amplitude sinusoidal signal source, whose phase phi m is determined by this signal VSM. Now the output of this block is a fixed amplitude sinusoidal waveform, whose phase has 1 to 1 uh, correspondence to the assembled n bit symbol, and the phase can be changed once per symbol time. Means this phase could be changed only once per symbol time, is TS or NTB, whatever. So this, in this way, we have to be generate the PSK, memory PSK signal from the bit stream. First, it would be converted to the serial, use the serial to parallel converter. Now the n bit data is available parallelly to the digital to analog converter. Digital to analog converter would be converted into the analog symbol, and that analog symbol is one of the 2 raised to power n possible symbols are there, and this voltage signal would be then applied to the constant amplitude sinusoidal signal source that would finally generate the output of the fixed amplitude sinusoidal waveform. And the phase is here 1:1 corresponding to the assembled n bit data, that is 2 pi upon m. Now after generation of the MRE PSK signal, this is applied to the receiver end. So the receiver structure is very much similar to the BPSK and QPSK. Only the squaring circuit has been converted into the raised input to the mth power. So here it is a coherent detection where we have to be locally regenerate the carrier signal that is similar of the carrier signal used in the transmitter section. So here again this MRE PSK signal is applied to the demultiplexer, and another part of the signal is applied to the this section, that is where we have to be locally regenerate the carrier signal. So first of all, it would be this carrier recovery circuit, you can say, where it would be signal would be raised to the input to the power mth power. Then it would be passed through a band pass filter that is tuned to the frequency MF0, and this band pass filter would only pass the signal of having MF0 frequency, and rest of the signal would be rejected, as well as the DC component of the signal would be also discarded, and this MF0 carrier signal would be further fed to the frequency divided by M, and this frequency divider network would be divided this by M, and finally we have to be available the carrier signal that is same as the carrier signal of the transmitter, and this carrier signal would be applied to the product modulator along with the splitted received PSK signal, and here the odd and even component would be separated out, and you can see that the cost function would be with the even symbols, and sign function would be the odd symbols are there, that would be further applied to the integrators, and integrators would be integrate, you can say it is a correlator also, integrate this odd and even signal components over the signal time period that is mentioned in this particular block. Noted, please note down this diagram or take the screenshot. So this is integrated between, you can see 0 to NTB time period for this particular two indicators for the odd and even symbols respectively. Output of this integrator would be PE and PO, odd and even signals would be came out. These are the voltage signals whose amplitudes are proportional to the TS P and TS P naught respectively, and change at the rate of the symbol rate. And this output odd and even symbol would be applied to the analog to digital converter further, and this would be converted digitally, and these signals having the n number of bits that is applied the parallelly to the parallel to serial converter, and this n number of bits of data would be then converted to a 1-bit stream, that is BT, that is similar the bit stream that we have used in the transmitter section. So this is a very common procedure for all receivers that we have learned, BPSK, QPSK, and MREPSK. Once you have understood one of the receiver function, you can derive the or explain rest of any two receiver that is based on the PSK technique. Only you have to remember that carrier recovery circuit, the power, M power, second power, a squaring circuit or fourth power like this, depending upon the type of PSK technique you are deriving. Okay, so this is all about the Emery PSK. Now we have to little bit insight on another technique, that is Emery FSK. So also like the PSK, we have possible to generate the Emery FSK modulation signals. So if you have to see Emery FSK communication system, it is an extension of the binary FSK system. So at the transmitter, n-bit symbols is presented each TS to an n-bit digital to analog converter, and the converter output is applied to the frequency modulator, that is a piece of hardware which generates a carrier waveform whose frequency is determined by the modulating waveform. So here only the carrier signal would be modified or modulate with respect to the applied modulating waveform signals. So you can see the transmitted signal for the duration of symbols interval is of you can say the frequency of f0, that is up to the fm-1. Here again we have combined the n symbols, so the relationship between the symbol and the bits are m is equal to 2 raised to the power n. So now see the block diagram of transmitter and receiver on a single diagram for the Emery FSK. So you can see the explanation of this also. Please take the screenshot of this particular diagram. So if you have to refer this block diagram where I have shown the half of the section, left side of this dashed is transmitter and right hand side is the receiver of Emery FSK. So you can see the binary data there is digital signals of n bit D0 to Dn-1 is applied to n bit digital to analog converter, and that would be converted this n bit data into a single analog signal that could be any one of the n bit data is there, and that would be further converted output is applied to the frequency modulator, that is nothing but a piece of hardware that generates a carrier signal whose frequency is determined by modulating waveform. Okay, so please note down this diagram. So output of this frequency modulator is nothing but a Emery FSK signal, and this signal is further applied to the through the channel, and it would be received by the receiver section. In the receiver section, you can see that incoming signal is applied to the M parallel, because we are here developing the M number of symbols. So M parallel band pass filters, and every band pass filter is tuned to the from f0 to fm-1 frequency, depending upon the number of symbols we are receiving. So this M parallel band pass filter is followed by each band pass filter is followed by every envelope detectors. So after band pass filters, you can see there is an envelope detectors is used, and this band pass filter having a center frequency, it is mentioned already in the diagram, f0, f1 up to fn-1. The envelope detectors apply their outputs to a device that would be a decision device actually, and each determines which of the detector indications is the largest, means which envelope detector's output is largest, that would be selected by this decision device. That's why it is then select largest output, and this largest output is then selected and transmitted to the n-bit analog to digital converter. Then again this analog signal would be reconverted into the n bits of digital data string D0 to Dn-1. So in this way we have used the n bit of digital signal bit stream and converted into the analog form, and then done its modulation with the help of the frequency modulator, And as per the symbols nature or the voltage levels, the its frequency would be modulated, and then further modulated FSK signal would be uh, passed through the channel and received by the receiver, where m numbers of the band pass filters followed by the m numbers of the envelope detectors are available, and that would be finally generate the or select the largest output through the decision device, and this is fed to the n bit A to D converter, and finally we have to receive the n bit of the digital data back that we have used in the transmitter section. So this is about the transmission and receiving of the M-Array FSK. Now we have to be see a little bit insight in the uh, geometrical representation of the M-Array FSK. So if you have to be see the signal space representation, so this is the signal space diagram of the M-Array FSK. You can see there is a more than 2 carrier signals has been shown here, because here the carrier signal would be modulated according to the incoming symbols. So you can see here there is a 3-dimensional signal space diagram has been shown. In one of the axis having the orthogonal signal U1, that is cos omega 1 t, frequency is omega 1. Another is U2, that is having the frequency omega 2. This third one is the U3, that is having the frequency omega 3. So because here the multiple frequency components are available for the M-Array FSK, there is a 3-dimensional representation of signal space diagram has been shown, and each signal point on this carrier axis would be separated from the origin by the amount of square root of ES. So there is a m mutually orthogonal coordinate axes are there. There is only 3 has shown, but there is a possibility of the m mutually orthogonal coordinates axis, and the signal vectors are parallel to this axis. So each signal vectors are located apart under root of square root of the ES from the origin. So distance between the 2 signal points could be calculated like this. This dashed line is shown. This is D, equivalent distance. So this could be easily calculated with the help of the Pythagoras theorem, you can say. So D is equal to square root of 2ES. This is the Euclidean distance of the signal point in the M-Array FSK modulation. And if you have to see, the Euclidean distance is greater than the M-Array PSK. So that could be written like this: D is equal to square root of 2ES or square root of 2NEB, because it is, if you have to be represented in terms of bit, it would be NEB. Similarly, we can also find out the bandwidth of the M-Array FSK. So see the bandwidth here through the spectrum of the representation of the M-Array FSK. So this is the spectrum of the M-Array FSK there, and from this spectrum you can see that each lobe is centered at a frequency. F1 is equal to KFS, F2 is K plus 2FS, like this, F3 K plus 4FS, like this. It would be increases the center frequency, you can say the coefficient would be as whatever the denominator is, suffix is there, you have to be increased by the 1. Okay, so in this way, if you have to be see, it would become as the bandwidth is coming on 2fs. It would be coming as a 2fs, or here also you can consider it is also coming at 2fs. So the distance between the 2 consecutive center frequency, you can see the bandwidth of this. So it is, bandwidth is 2fs or 2mfs, because there is a M-Array signaling to 2mfs. So fs is what? FB upon N, and M is 2 raised to the power N is here. So finally you can define the formula of bandwidth for MRE FSK is 2 raised to the power N plus 1 FB upon N. Actually both are same, only we have converted M into the N, nothing else. It is 2 into 2 raised to power N means 2 raised to power N plus 1 Fs, and Fs is further written as in terms of FB upon N. So this is the spectrum of the MRE FSK and the bandwidth equation. So this is all about the MRE techniques, either for the PSK or FSK. Tomorrow we would be learn about the QASK technique. That is also very important technique, or it is also called as a quadrature amplitude modulation, QAM. So, and that is the last topic of this unit. Okay. Now, after this, we have to be take a little bit insight of the practical of you can say QPSK. That is 2 practicals are remaining actually. So one of them